Hello, and welcome back to another session on data mining. So, in preparation for our discussion on principal component analysis and other types of dimensionality reduction methods, we've gone through a set of preliminaries. We have discussed uh, Lagrange multipliers, or McDonald, right? And we've also talked about what is the relationship between each of the following concepts. We've talked about vectors, matrices, distance, Euclidean distance, for example. We talked about dot product. We've talked about projections and how matrix vector products can be interpreted as transformations. We've also talked about eigenvectors. We've talked about variance and how that is related to information. We've talked about correlation, covariance, and the covariance matrix, which is essentially the matrix of if you have like n variables or d variables, then you have their pairwise uh, their pairwise covariances can be expressed in the form of a matrix. So let's say if you got three variables, then you get a 3 by 3 matrix in which the diagonal values are the variances of those variables, and then the off diagonal values are the covariances of different pairs of variables. So we talked about that. We've also talked about covariance and how it's related to information. And now I think we are in perfect position to begin our discussion on principal component analysis. So if you've already studied principal component analysis, it might be a bit easy for you, but it might be a good idea that you go through these topics that we've covered in previous videos prior to moving on to principal component analysis. We're going to take a very simple, a very gentle approach to dimensionality reduction. So what this word dimensionality reduction means is the following. So remember, we expressed each example we had instead of in the form of a few features. So typically, what we are given in machine learning is a matrix of size n cross d. There are n examples in total, and each example is in d dimensions. So this is a number of features. And by dimensionality reduction, we mean that we want to reduce this number from d to a number less than d. Let's call it d prime. So let's say if you got an image and the image is of size 100 by 100 pixels, then that means the number of dimensions for that data is equal to 10,000. And that's a pretty large dimension set. And what we want to do is to utilize the correlations between different features to try to reduce this number from, say, 10,000 to a manageable number, let's say 100, for example. Okay, so this is called dimensionality reduction, and there are a number of reasons why we want to do this. We haven't discussed that in too much detail at this time, but these are going to make those reasons are actually going to make more sense once we have talked about the methods used for dimensionality reduction. So we are going to start with principal component analysis, and then we're going to talk about different other approaches as well. However, if we want to do very naive type of feature reduction, then what we can do is, let's say we've got a two-dimensional machine learning problem in which we have two features. Okay, so there's a feature along this axis, and then there is a feature along the vertical axis, and we've got a bunch of data given to us. The simplest way we can reduce the number of dimensions is simply to drop one of the two dimensions. So what that means is that, for example, if you've got a point given over here for which you know the feature values of both of them, then what you can do is, instead of storing both of these values, let's say if this is, for example, let's say 10, 7, then we can reduce this to a single value, which is 10, right? So we can keep only one of the two features. And this is the naive way of doing dimensionality reduction. It's called feature dropping. So you simply reduce the number or the dimensionality by dropping anything else that you don't want in there. Okay. So that's one way of doing it. And we can understand dimensionality reduction even in this one that we've talked about, simply dropping the features in terms of projections. So if you think about this particular dimensionality reduction that we have done, so we represent, instead of having 2 points for each example, we reduce one of the dimensions. So it reduces this. Then we can think of it like if you're projecting this point, that is 10, 7, along one of the two axes. So if I project this point onto the horizontal axis, then this value is going to be 10, right? So if I project this point to here, then that can be interpreted as a way of doing dimensionality reduction. So projections can be used for dimensionality reduction. That's the main lesson here. So let's say we got this point, we can project it over here, and then we got this point, and then we got this point mapped over here. And we can express this mathematically by simply doing a projection of a given point x along a vector, which is w. And if the vector is 1, comma 0, which is the unit vector along the horizontal direction, then that means we are only left with the first feature. So let's say if we take the point 10, comma 7, and we multiply it with the first, with this direction vector over here, which is 1, 0, then what we are gonna get is 10. Okay, and that is one way we can reduce the number of features. If I want to project this point along to this axis, we can consider it as a dot product of x with the unit vector along that direction, right? So we can now relate that we can reduce features by doing by dropping features, and that can be achieved through projections, right? But once we make that projection, let's say if I project this particular point, that is 10, comma 7, onto the x-axis, then I essentially am losing the second component, which was 7. So I'm losing all information uh, that was available to me for that particular axis, right? So that is there's an amount of information loss involved, and we can relate data dimensionality to information loss. Whenever you reduce the number of features, you can expect that this is going to be a lossy compression, or you can think of it like you're going to lose certain information. Similarly, when I project along to the y-axis, we also lose some information. So which feature should I drop out of these two? That is an interesting question, and I welcome you to pause the video here and think about it before moving on. Okay, we can answer this question about which feature we can drop for this particular data set by considering how much information we lose when we disregard or when we throw away one of the features. Let's say if I throw away the feature along the x-axis, that means I will project everything along the y-axis, then this point is going to be projected over here, okay? This point is going to be projected over here, and so on, right? So that is the amount of that is what we are retaining for all of those data points. Now, as you can see, there can be multiple points that get mapped probably to the same location on the y-axis or very close to each other, even though they were different along this horizontal axis. But that is information that we are losing. So if you think about it, the amount of information that we are losing is actually this much if we are projecting all the points onto the y-axis. So that's why we call it variance lost. So this is the amount of information or the amount of variance that we are losing. So this is the amount of spread that would be lost if everything was projected onto the y-axis. Similarly, if I project everything onto the x-axis, then this is the amount of variance that is being lost. And to answer the question, which of these two features we can drop with minimum loss in information or with minimum loss in variance, you can simply compare the magnitude of the variances that you have over here. So how much variance we have here and how much variance we have along this axis, and whichever these number comes out smaller, you can throw away that particular feature. And that follows from intuition as well. Like if we had data like this, let's say like this one, right? And if I projected everything along to the y-axis, right, we wouldn't lose any information because all the information, all of these points had the same value for the x-axis, right? So that information was redundant. So the variance along the x-axis for this particular data set was 0. Therefore, there was no information loss involved when I projected all of these points onto the y-axis, right? Similarly, for this particular data set, if I project everything along to the x-axis, then I wouldn't have any information loss along by dropping the y-axis because that is redundant. So by redundant information or redundant features, what we mean is that those features have have the same value for that particular point, or in other cases, the variance of this feature along the y-axis, the feature along y-axis is 0 or close to 0. Okay, so we can now relate the concept of redundancy to information theory, and we can also relate it to variance. The more redundant the data is, the lesser the information, and the lesser the amount of variance, right? So uh, that's the major lesson here, okay? And if we talk about this very simple or very naive approach of dropping features to reduce the number of features, then we can simply measure how much information we lose by simply measuring the loss in variance but due to a projection. And in this case, we are essentially projecting onto the canonical axis. Okay, here's a trick question for you, and you are welcome to pause the video and think about it. In which case, think of a data set in which if you project along to the x-axis, there would be no information loss. And if you project along to the y-axis, there would be no information loss. I've given you some examples like this one and this one, but can you think of others? Okay, so that's something that would help you understand this in a bit more detail. So what we've covered so far, is projections can be used for reducing dimensions, right? So if you project along to the x-axis, we have all we are left is the data points along the or the information along the y-axis. Along the x-axis, and we've lost everything along the y-axis, right? So can we do better? So instead of doing canonical projections along to the x or y-axis, can we find a vector so that if I project my data, all of this data that we have over here, along that vector, the amount of information that is being lost is minimized. Okay, and we can do that. We can think about that. Let's say if I take a particular data set like this one, and if I project everything, then there is a certain amount of information lost when I make this projection. And if I project everything along this axis, then there is a certain amount of information that is lost, right? Can I project my data, let's say, along another axis? Let's say, what happens when I project my data along this vector? There's going to be some information loss, but is that information loss going to be larger or smaller in comparison to when I was projecting along this axis or when I was projecting along this axis? That is the thing that we would be doing. We would be trying to find those directions so that if I project my data along those directions, the amount of information loss is minimized. And if you think about this problem intuitively, then it becomes really easy. Let's say we've got data that is spread like this. You have got two features, one along the x-axis and one along the y-axis. Then if I project all of my data along the horizontal or along the vector 1, 0, we have a certain information loss, right? And if I project everything along the y-axis, then I have a certain information loss. So the projection along the y-axis will be done onto the vector w is equal to 0, 1, and this is going to be w is equal to 1, 0. So what happens if I project everything along this axis? Okay, so first of all, we need to specify what this direction is. And that's pretty easy to do. We can take any point on this along this vector, let's say 1, 1, and we can make its norm to be, because if we want to specify the direction only, so what we can do is divide this vector by the norm of that vector, which is square root of 2. And what this means is that this direction vector is going to be 1 over square root of 2 and 1 over square root of 2. So this specifies the direction along this particular line. And if I project all of my data points along this line, then we have all of this information, right? So we're trying to capture information from both of the axes, both of the original axes, and this is going to be the amount of information that I would end up losing. Another way of thinking it is what I'm going to describe right over here. Let's say if you got a single point over here and you have a certain value, let's say AB. So its value along the x-axis is A, and its value along the y-axis is B. So if I make a projection along the x-axis, then the amount of information that is being lost is like we'd lose this feature, right? And if I project along the y-axis, then I'm losing the value along the x-axis. But once if I project it along 1 by square root of 2 and 1 by so we do that essentially by taking the dot product of this vector with this direction vector, and that is going to come out to be 1 over square root of 2a plus 1 over square root of 2b. Now, if you think about it, both of these feature values, the original values, are being considered in this projection, right? So we have a projection that contains both of the original features, but it is a scalar, right? So that's the good thing about this particular projection. Another way of thinking about projections is so once we make a projection of a single point, let's say along this axis, and I know what this axis is, right? So I can make a projection of this point onto this axis, if I know what that vector is, if this is, let's say, 1 by square root of 2, and this is 1, the y component is 1 by square root of 2, as long as I know this vector and I know what the projection is, I can go back and reconstruct the point. And that's going to be really helpful, as we shall see down the line. Okay, so if we talk about data projections, then what we are essentially interested in is trying to find a direction in which we have minimum information loss. And that we see is going to be along the direction of maximum variance, because why? uh, Variance and information have a sort of a proportionality relationship, right? So if I project everything along this direction, which is the direction of maximum variance of this data, uh, that is going to incur the minimum information loss. Another way of thinking of it is just like we had these cases in the previous slide, that if I project everything along this axis, along the vertical axis, then the amount of variance that I lost was this much, and the amount of variance that is captured is this much if I project everything along the x-axis, and the amount of variance that is lost is this much, right? And there's going to be a certain amount of variance that is going to be lost when I project my data along this particular line, right? So let's say if we have, if you think of it like this, uh, let's say we take different direction vectors. So if you have a very naive implementation of finding the direction of maximum variance, what we can do is first we center the data right over here, and then I take a particular vector. I'm going to call it WP vector, and let's say when WP is horizontal, then I project everything along the horizontal onto this vector, and it's going to drop everything along the y-axis, right? And once I make this vector perpendicular, or take this vector along this direction, then I'm essentially going to drop everything along the x-axis, right? And I can move through these. I can rotate this vector, and I can make those projections, and I can calculate how much variance I am capturing. So let's say if I project everything along the x-axis, then we've got original point x. We multiply it with a weight vector, or direction vector called w, and we get a projection value which is called z. So if I do it for all the points that are given to me for I is equal to 1 to n, then I am essentially converting all of these vector points on into scalar values, and I can take the variance of all of those scalar values. If that variance is large, probably that's good, because that means that the direction vector that I picked will incur minimum information loss, because we have reduced the number of features now. Okay. Similarly, however, if I pick a direction W in which after projection the variance is small, then what that essentially means is that particular direction is redundant, or those features are redundant, and there is not much information contained in that. But the real question is, how do we find this direction of maximum variance? So what we can do is try out like we can do it exhaustively. So we start with a line along the horizontal. We pick p is equal to 0, and then we go from p to pi, p is equal to 0 to pi, and let's say a specific number of steps, let's say 10 steps, and we calculate the projection vector. When we have p is equal to 0, then this is going to become 1, 0, and as I increase the value of p, we are going to gradually move to minus 1, 0. Okay. So there is going to be 0, 1 along the way as well, and there are going to be all other direction vectors that we can calculate using this formula. And once we have a direction vector, I project all of those points that are given to me in the data set onto that projection vector and calculate the variance. And then what I do is, for each value of this angle, which is measured in degrees, let's say, we can calculate how much variance is in that direction, and we can perhaps identify where the maximum of this occurs, and that's going to give us the direction of maximum variance. And that is going to be the direction, so that if I project my data in that direction, the variance is maximized, so that if I project everything along that direction, the amount of variance that I lose, or the amount of information that I lose, is going to be the smallest. Okay, so you can use this way of use this naive implementation of doing optimal feature reduction or dimensionality reduction, but it's going to be computationally very complex. So what should be the step size should I use? And what if I have a large number of features and I want to, let's say, go from 10,000 to 100 features? How do I actually do that? That's going to be really computationally intensive. Fortunately, there's a more mathematical way of doing the same thing. But to be able to understand that, the first thing that you must wrap your head around is why are we projecting along the direction of maximum variance? And based on our previous discussion about variance, we have, I hope you are clear about the relationship between variance and information. So if I pick a direction such that there is no spread along that direction or the variance is zero, then that means there is no information content there and I can probably discard that dimension. Okay. So moving on, after that, once we have this variance captured, so let's say if we do this experiment, and I'm going to give you the code to do this naive implementation. So if you have got a data set like this one, so you've got a height and a weight value, and these are normalized between to a mean of 0 and a standard deviation of 1. And then what happens is that as we rotate the W vector, the projection vector, and then we project all of the data onto that and calculate the variance, this is what it comes out to be. And we can see that the variance is maximized at an angle of 45 degrees. And if you take the cos of 45 degrees and you take the sine of 45 degrees, that comes out to be 1 by square root of 2, 1 by square root of 2, which is essentially the same direction that we had found through our visual analysis. Okay. So PCA, what we talked about is projections, essentially dimensionality reduction. And PCA is a way of doing that. So it's a method of transforming the data essentially, so that we project the data that we have along the direction of its maximum variance. So let's say if you got this particular data set, then the first principal component is going to be along the direction of maximum variance, which is probably the direction vector that I've drawn in front of you. So we project everything onto this, right? Okay, so that's going to be the first principal component. And then the second principal component is going to be the in a direction that is orthogonal to the first one. It's going to be in this direction. Okay, so you can think of it that the original axis that was given to us, let's say for this particular point, we had a feature value along the x-axis and we had a feature value along the y-axis. Let's say if this was a point A, B, then what we have done through what we will do through principal component is we will project these points or each of these points onto a different coordinate system so that now this point gets mapped onto this value along the first axis and this value along the second axis. Okay, so we will map AB to something A dash B dash. Okay, so that the amount of variance along the first direction is going to be much larger in comparison to what it was along the original feature vector. And then if I can, then what I can do is I can probably drop off certain dimensions in which the variance is zero or in which directions the variance is low. So if someone asks you, if you walk into an interview, what is principal component analysis? Principal component analysis is essentially a method of transforming the data along to directions of maximum variance. The, it's not a it's not a dimensionality reduction method per se unless you apply a cutoff on the number of dimensions. Okay, so let's say if you got a bunch of data, what you do is if you can plot it, you can identify the direction of maximum variance manually. Like this is the direction of maximum variance. You can identify the vector, the first principal component, and then you can take a direction orthogonal to it. And then what that means is that instead of having data like this, you have data like this, so that the first direction that you have has a larger spread, okay, in comparison to the second one. So some people find it difficult to understand mathematically, but if you do it geometrically, it's going to be much more easier. And for that, what I welcome you to try is to take a piece of paper and put some points on it, just like what we've done. And then take a scale or a selenite crystal if you have it, and measure how much spread there is along this axis. Okay, and let's say for this particular case, it's going to be this much spread. And if you take the spread of this data along this y-axis, then the amount of spread is probably going to be this much. Then identify the direction of maximum variance, which is this one, okay? And measure how much length this is. And and we know from the Pythagorean theorem that this particular length is always going to be larger than this one, and it's going to be larger than this one. So this direction that we have identified, which we are calling the first principal component, is a direction in which the variance is actually larger than the variance along the original axis. So let's say if we calculate the variance along the original x-axis, and I call it sigma x squared, and I call this variance along the y-axis of the data as sigma y squared, then the total amount of variance in the data is going to be sigma x squared plus sigma square y, because the two directions are essentially perpendicular to each other. So this is going to be the overall variance that I'm going to call sigma square for this particular data set. Now, when we apply principal component analysis, we've essentially transformed this data from a two-dimensional data set into another two-dimensional data set. But we have rotated the axis. So the first principal component that we're going to get there is going to be a certain amount of variance along that direction. And I'm going to call that sigma square 1 because it's along the first direction. And this sigma square 1 for this particular data set is going to be larger than sigma square x. I've just given you a visual proof of that. And the variance along the y-axis is always going to be sigma square 2, which is how much data, how much spread there is along this one. Now, the variance of sigma square along the first principal component is going to be larger, but the variance along the second principal component is going to be smaller. You see this spread is smaller along the y-axis, along the new y-axis, okay? And you can see it over here in this plot as well. So this is much smaller, right? But the good thing is, if you apply a principal component, it's essentially a change of axis, and the amount of total variance is always conserved. So sigma 1 squared plus sigma 2 squared is going to be exactly equal to sigma square x plus sigma square y. That means by transforming the axis, we actually haven't lost any information. Information loss or dimensionality reduction occurs once we drop the features along, once we do a dimensionality feature or a feature drop in the principal component space. So let's say if I drop off the features, if I drop everything along the second principal component, then I'm going to have some information loss. And the amount of variance along the new direction is just going to be sigma square 1, which is actually going to be smaller than sigma square x plus sigma square y. But this is going to be better than if had I chosen to project onto only the x-axis or only onto the y-axis. So that's why this principal component analysis is so much fun, and it's so much very well used in the field of data mining and machine learning. It identifies the direction of maximum variance so that we can reduce the number of original dimensions with minimal information loss. Okay, so I hope you have a good idea of how this is being done. But if you think about it, what we really want to do, or what we've done earlier and using our naive algorithm over here, is we started off with something at the horizontal, and then we kept on rotating it, rotating until we found the direction of maximum variance. So every time we did a rotation of the axis of the projection axis, we also went ahead and calculated the variance of the data after the projection, right? And then we plotted it across all the values of theta over here, and we calculated what the maximum variance direction is, and that is the direction you want to project your data into, right? So essentially what we want to do is we want to calculate how much variance there is if I project my data onto a projection vector W. So let's say if you got a data point or a bunch of data points, and I'm going to call these X, okay? And you've got a vector W, so that if let's say if this vector, then what we want to measure is we want to measure how much variance does the data have after the projection. So if you got a data point, let's say Xi, and we've got a vector Wt, then after the projection of Xi onto W through the dot product, let's say we get Zi, which is going to be a scalar now. What we want to do is calculate how much variance is there across all the points along this, after the projection onto this W vector, okay? And that is what we are going to work out right now is a mathematical formula that essentially gives us a way of calculating how much variance we have if I project my data along this W. And because the formula that we are going to get is going to be really simple, so it's going to accelerate the calculation of the direction of maximum variance. So we wouldn't need to use that naive method that we just talked about. And it's really simple. We know that we are projecting the data, and after the projections can be expressed as dot products, and we want to calculate the variance after the projection. So the variance of all the data that we have after the projection is going to be the variance of all the data with the dot product W with W. And we know that the formula of variance is, we know that sigma square is nothing but the expectation of x minus mu of x, right? So we subtract everything and we square it, right? Since this we are calculating the variance of z in this case, which is W transpose x, what we do is we calculate W transpose x, we subtract it from W transpose mu, which is the mean of the data, and then we square it, right? And a square can be expressed like this. We just need to write it twice probably, and then we do some rearrangement so that we take W transpose out on this side, and then we calculate the W transpose, the W out on this side, because W is independent, but this is something that we are providing, because this is the vector that we want to project on. That means we can move it outside of this expectation, right? So whenever you see expectation, replace it with a sum, with a scalar divisor. Okay, so it's, if let's say we had W1, WA plus WB, you would be able to write it like W times A plus B, right? So this is the exact same thing that we've done over here. We'll be moving W transpose out over here, and we'll be moving W over here, and then we'll move the expectation in, which would come out to be this thing. And if you've seen our previous video on covariance matrices, then what this is in the middle is the covariance matrix of the data, and we call it C. So this is the proof that shows that the variance of the data after you project it along to a direction W can be expressed very simply as W transpose C and W. Now, the good thing in this is the only variable we have is W, because for a given data set, the covariance matrix is going to be fixed, right? We need to calculate it once, and then what we can do is we can calculate the variance by changing W, and then we can solve the problem, the optimization problem that we are trying to solve, that is maximize, find me a direction W, so that the variance of my data after projection along that direction is maximum. Okay, so that's really nice. And we know that the variance of Z is going to be nothing but W transpose CW. So that's what we want to maximize, right? So we want to find W so that the variance of Z is going to be maximum. And now we have a closed form formula for it, right? That's cool. But there's a slight problem. We also need another constraint, and that is going to be W transpose W is equal to 1, so that it's a direction vector. So what this is essentially the norm squared of W should be equal to 1.0. Okay? So because otherwise, if you simply want to maximize this thing, then you would end up with W is equal to infinity. So if you're having trouble understanding this bit, then I suggest you consider the following. Let's say if you want to maximize with respect to W square, then the solution to this optimization problem is W is equal to either minus infinity or W is equal to plus infinity, because there is nothing bounding the magnitude of W. That's why we need this to be a direction vector. So if you relate it to our previous example of Old MacDonald, let's say if you wanted to maximize the area without, he had infinite wire length, then we would always all be living in his farm right now, because yeah, his farm would have infinite area, right? So the same thing goes over here. What we have worked out right now is a formula that gives us the relation between the variance of projected data along a particular projection vector W. Okay, and now we can formally define what principal component is. It's just like almost every other machine learning model. There's a optimization problem hiding under it. We want to find a unit vector, W, that maximizes the variance along the projection. So we want to maximize the variance along the along Z1, such that the projection W1 transpose W1, or the norm of W1 squared, is equal to 1. And this is a constrained optimization problem, right? So we know now that this is going to be W transpose CW, right? C is the covariance matrix, and now we have this. And then we use the Lagrange or multiplier method to convert this constrained optimization problem into an unconstrained optimization problem. If you are having trouble understanding this, please go and watch the video and see how McDonald was able to maximize his farm area, right, or his barn area, right? But what we essentially do is we have an unconstrained, we take the optimization objective of the unconstrained optimization problem, and then what we do is we calculate uh, we add another variable which is called Lagrange multiplier, and then we add the constraint over here, which is in this case W transpose W minus 1 is equal to 0, right? So this is coming from here. And now what we do is if we can take the derivative of this and we take the derivative of this with respect to W1 because we want to find the direction such that if I project my data along that, we're gonna get the maximum variance, right? So if we take the derivative of this and substitute it equal to 0, then this is how I'm gonna do it. We take the derivative of this whole thing with respect to W. We've got W transpose CW minus alpha times W1 transpose, W transpose W minus 1, okay? And this is gonna be come out to be CW, okay? And this is gonna come out to be alpha times W, okay? And if you substitute this whole thing to 0, then that means this is going to be CW is equal to alpha W. Now, alpha is a scalar, W is a vector. This W, of course, is the same thing. So it's a vector, and this C is a matrix. So a matrix being multiplied with a vector leading to the same vector with only a scalar change in, in it is called an eigenvector, right? So you can go ahead and take a look at the video for eigenvectors. So what this means is that if I can find the eigenvectors of this covariance matrix C of the data, then essentially what I found are the directions. If so that if I project my data along those directions, I get maximum variance, right? That's pretty cool because now I don't need to use those naive methods, and the only thing I need is the covariance matrix of the data, and I need a way of finding the eigenvectors. And we already have really good libraries to find eigenvectors and eigenvalues, right? So what this means is that this problem of maximizing variance along the projected direction subject to this norm constraint can be interpreted as an eigenvalue problem, which we know how to solve, right? So that's what we're going to do, right? Okay. So W is the eigenvector corresponding to the eigen covariance matrix with the eigenvalue alpha. Okay, so that's really nice. So this is uh, how PCA works internally. You're given a data set, okay, in which you have n samples, and each sample has d dimensions. Okay, and what you do is you first normalize the data, you compute the covariance matrix of the data, and you calculate its eigenvectors, and those eigenvectors become your principal components, and then you project all of your data along those direction vectors, and you would, if you drop some of those uh, features after projection, you wouldn't lose that much information. So this is an algorithmic view of how PCA works. So if you think about this as a black box, what you're feeding in is an X, which is of size n cross D. And if this is PCA, then what it gives you is actually a matrix of size D cross D. So that, and each of these is going to be an eigenvector of the covariance matrix of this X. So what it would do is first it would compute the covariance matrix of X, which we are going to call C, and we know how to do that. And then we are going to find the eigenvalues of this C matrix. And that's how we're going to get this eigenvalue decomposition, which is going to give us W's. So it's a really simple algorithm, really fast, and here we're gonna see it in action, and I'll give you a Python notebook that actually implements this, so it should be easy for you to understand. Let's say we've got our normalized heights and weights over here, and what we do is we take the we calculate the covariance matrix, which comes out to be 1, 0.96, 0.96, and 1. And what this tells me is that if I find the eigenvector of this particular covariance matrix, that comes out to be 0.7, 0.7, which is, I hope you remember, 1 over square root of 2, 1 over square root of 2, which is this direction over here, right? So that means if I project everything along this direction, then I get this particular feature, right? So I've done a change of variables over here. So instead of writing height, now it says PC1, which is the first principal component. And I can calculate the second eigenvector of this matrix, which comes out to minus 0.70171 and 0.7071. Or in other words, minus 1 by square root of 2 and 1 by square root of 2, which is going to be a vector with like indicated by this blue line over here in this. And if I project all of the data, then I get the second principal component, which I can show over here. And you can see that the variance along the first direction, or the spread along the first direction, is much larger in comparison to the second one. And we can calculate that. If I make the projection and calculate the variance, then the amount of variance along the first direction is actually, it comes out to be uh, 1.96, and the amount of variance along the second one is going to be 0.04. So in this particular case, the variance along the original height value was 1 because we had normalized it. So sigma square height was 1, sigma square weight is equal to 1.0. So the total variance was is equal to sigma square W plus sigma square H, which comes out to be 2.0, right? Now, once I do this projection and calculate these variances again, then these come out to be sigma square 1 is going to come out to be 1.96, and sigma square 2 is going to come out to 0.04, and if you add these together, you're going to get 2 again. So no loss in variance. But the good thing is, now I can drop out this principal component number 2 and use only principal component number 1. So I've effectively reduced the amount, the dimensionality of my data from 2 to 1, and the amount of information loss, I can calculate that actually. The amount of information loss is going to be this much out of 2. So the amount of information that I would lose by projecting only along to the first principal component is going to be 0.04 over 2, or in other words, because 2 is a total variance over here. So that means 0.02, right? And that means if I multiply it with 100 to convert it into a percentage, then that means I've only lost about 2% of the variance. And the reason I was able to do that is because these two variables, height and weight, were very strongly correlated with each other, which I saw in this covariance matrix, right? 0.96. Okay, so whenever two things are highly correlated, and that means that I can recover one thing from the other with minimum loss of information. If two values are exactly uh, positively correlated with the correlation score of 1.0, then I actually don't lose any information, even if I throw one of them away. Okay, and another good thing is if you look at these particular values W1 and W2, then if you take the dot product of these two, you would see that the dot product of these two eigenvectors that we have calculated is going to come out to be 0. And what that means is that these two eigenvectors or these two directions are going to be orthogonal, and you can see that over here in the plot as well, right? So if you write the principal component matrix in this case, or W, it comes out to be that is going to be the first vector, 0.7071, and the second one is going to be minus 0.71 and 0.7. Okay, and if you take the transpose of this and you multiply that transpose with this W, you actually get an identity matrix, which means that this W is actually its own, its transpose is its inverse as well. So what that means, I can use the transpose of this to move everything back into the original space. So I can go back from the principal component space into the original feature space. Okay. Now here's a trick question for you. So if we haven't been able to understand anything, and the only thing you understand is we should be projecting data along to the directions of maximum variance, you should still be able to solve this quiz. Okay, and I welcome you to pause the video and identify the directions of maximum variance for each of these data sets. So for example, for this data set, the direction of maximum variance is going to be this one. It's probably going to be this one. In this case, we're not so sure. It can be this one, probably. In this case, these two variables, let's say we call them variable 1 and we call them variable 2 on the y-axis. And these two variables are anti-correlated with one another, okay, so or negatively correlated. But the direction of maximum variance is going to be this one, and similarly, we've got a maximum variance direction over here. In this case, there is perfect correlation, and the direction of maximum variance is this one, right? Again, pause your video and think about what happens in these cases. Okay, and I leave that to you to figure out what are the directions of maximum variance for each of these data sets. Okay, it's important to understand the following. If you want to give yourself a review, how do we convert an optimization problem of finding the maximum variance uh, that lies at the heart of principal component analysis into an eigenvector problem? That's the mathematical bit of it. It's more important to understand at an intuitive level why we are projecting the data along the direction of maximum variance. The rest is mechanics, right? And there are really excellent libraries available out there that allow you to do all of this in a jiffy. But but we need to be able to understand this in a bit more detail. Okay, so we've covered all of these that we've essentially lose 2% variance. I just put it in the notes for you to follow on. Okay, so we've covered this as well, except for the proof, but that's essentially it. And we can use dimensionality reduction, right? One of the reasons we want to do dimensionality reduction of a given data set is for visualization. Let's say we've got a data set of numbers, right? And each number is expressed as an 8 by 8 image. So the number of dimensions in this data set is going to be 64. And if I want to do a scatter plot of all of the data points so that I want to show zeros over here, let's say, or where do the zeros go and where do the ones go, I wouldn't be able to do that because the number of features that I have is pretty large. It's not two. But what if I use principal component analysis to reduce the number of dimensions to two, and then we can use that as a scatter plot. So we can use this for visualization, right? And the way we can do that is pretty simple. This is how you would do it in sklearn. Let's say you import this PCA object from sklearn. You specify how many components you want. Let's say if you want to project on the data set you have is high dimension, but you want to use two-dimensional scatter plot, then you can specify this value as 2. You can fit your data set, fit your PCA to this data set, and then you can transform it, or you can use the same function called fit underscore transform to achieve the same effect in a single statement, right? So there's another function over here, but that's going to give you, now let's say if your original x was n cross d dimensions, and you specified your new dimensions or the reduced dimension to equal to 2, then after the projection, your z is going to be of size n cross d dash or n cross 2 in this case. Okay? You can also calculate how much variance you lose by determining something called a scree graph, and I'm going to talk about that in just a bit. But this is essentially all you need to do. All the covariance matrix calculations and all the eigenvalue problem calculations, scikit-learn is going to take care of that. But that doesn't mean that you shouldn't try to understand these concepts in a bit more detail. And the reason for that is not just PCA, but these concepts of calculating covariance matrices and then finding these eigenvalues and eigenvectors of these matrices underlie a large number of other machine learning problems and then a large number of other machine learning algorithms. That's why it's important. Okay. So I welcome you to pause the video here, understand the mathematics of it so that we can move on to using this data, to using this code to generate our plot, right? We need to generate a scatter plot of all of our data. And this is what the plot is going to look like. The part of it is going to be in your notebook. Now, what you see is that if you plot all of the zeros over here, so those remember each number is handwritten digit in this data set is expressed by in the form of an 8 by 8 image. So there are 64 dimensions in total, but we have reduced that dimensionality down to 2, and we so that we can see this this sort of scatter plot. So every point that you see, for example, this one actually corresponds to an image of a digit, right? So this is going to be a digit, this is going to be a digit. And what I've done over here in this plot is that I've colored each of these different digits with different colors. So we have zeros and nines in different colors, and then we have got, let's say, red is 8, So this, all of these digits are a bunch of eights. And then we have got zeros over here in black that you can see, and we've got nines in light gray. And what you see over here in this plot is really interesting to interpret and to make observations over here. What I can see over here is like if you look at all the zeros except for these ones, so this particular zero, let me use a different color here so we don't confuse any of the colors. Which color should I pick? Let me pick let me pick this dark red. Okay. So if you don't consider this zero or this one, which are actually sort of outliers from the rest of the other, then we can actually check whether they look similar to the rest of the data or not. But I can see that they wouldn't, right? And we can also see that all of the zeros are clustered over here, and then all of the ones are clustered over here. And it also shows that zeros are very different from ones because they are far away. All the ones are over here, and all the zeros are over here. So you can understand different types of structures in your data by doing such visualizations through principal component analysis, right? One thing that I must emphasize is that since we have reduced the number of dimensions, from 64 to let's say 2, there is going to be an information loss involved, and that's going to be true in any case, right? So 2 points that we see close over here may not be so much closer if we had one more principal component. So it's important to keep that in mind when interpreting these plots. Now, the next question we would like to ask is how much information is lost when we do this PCA. And I welcome you to try it out through the notebook as well. But I'm just going to briefly talk about it over here. If you pay attention to what these alpha values are, so these are the eigenvalues corresponding to the first principal component, and the first eigenvalue comes out to be 1.96. Then if you do the projection, the variance is also going to come out to be the exact same number. So these alpha values that we actually get are actually the variances along these data. So this is going to be the variance along this direction, and this much is going to be the variance along this direction. So this is going to be alpha 2, which is 0.04, and this is going to be the variance along the x-axis, which is 1.96. Okay, so because the way PCA works is that you've got a matrix of size n cross d, the data matrix. Based on that, you calculate another matrix, which is the covariance matrix of your data, which is going to be a d by d dimensional matrix. And then what you do is you calculate a W matrix, which is going to be a matrix of eigenvectors, which is going to be of size d by d again. But for each of these vectors, you're going to have an associated alpha value. So you're also going to get d alphas. And each one of these alphas is going to be the variance along that particular, if you of your data, if you project your data along that direction. So because your principal component analysis gives you these variances, then I can go ahead and use these to calculate how much information is going to be lost if I made a projection to say only the first principal component, or only the first two principal components, or only the first three principal components, and so on. And we can plot that in what is called a scree graph. It's a really strange name. I don't know why they picked that, but this is how it's done. If what we have is over here is that we have a number of eigenvectors, which the maximum number of eigenvectors we're again gonna get for this particular data set. If let's say we have got 10,000 digits, and we have got each digit expressed as an 8 by 8 image, so we've got a 64 dimensional data set. So the number of dimensions is going to be 64. So the number of eigenvectors we're going to get is 64 as well. And then what we can do is we can plot the eigenvalues we have. We can plot each eigenvalue over here. The first eigenvalue is around, let's say, 190 or something. We can calculate the second one, and so on. So we can generate a plot like this, right? So what this means is if I project everything only along the first dimension, so I reduce the dimensionality from 64 to 1, then this is the amount of variance that I would capture. That is going to be 195. But then I'm going to lose all the variance, or the sum of all of these variances, right? So we can express that as a percentage, and that is called proportion of variance explained. So this is really important to understand when you're using these libraries. So what happens is that you calculate essentially how much variance do you lose, or sorry, how much variance do you keep if you project your data onto only the first k principal components. So let's say if you're given a d-dimensional data set, but you only want to keep k principal components, then what you can do is you can calculate how much variance calculation is required, how much variance is proportion of variance is kept, and it is simply the ratio of the sum of the variances or sum of the eigenvalues, the first k eigenvalues divided by the sum of all of the eigenvalues. Okay, so this is what we express as the proportion of variance, and if for a given data you plot your k value along this axis and you plot your proportion of variance along the y-axis for a given k, then you get is what is called a scree graph, and which looks like this. So along the x-axis are the eigenvectors, and along the y-axis is the proportion of variance. And what this tells me is that if I keep 10, if I project my data on, reduce my dimensionality from 64 to 10, then I'm losing about 25% of variance, because the proportion of variance that is maintained is probably around 75%. Okay, so these plots are really important. Whenever you use PCA, don't use PCA without first thinking about these plots, because they tell you how much information you're going to lose when you have a particular, when you project your data along a certain number of directions. Okay, so this is what you can do. This is how you can generate this scree graph. Essentially, what we are doing is we are accumulating how much explained variance is captured for each given dimension, and then we are just plotting it. Okay. Okay, so that's really nice. So this is the algorithm. Just to summarize, you're given a data set of n examples, and you have each sample expressed in d dimensions. This is the data set you have. You first go ahead and normalize your data set, so you can calculate the covariance matrix like this one, and then you find the eigenvalues and eigenvectors of this covariance matrix, and then you project all of your data using this matrix W after you have selected whatever number of principal components you want to select, let's say k. Okay, so this is the classical method of doing principal component analysis, and the good thing about this method is that if you think about it like this, as I've been drawn earlier, you have x going in, and it spits out a w, which is going to be a matrix of size d by k, so that if you project your data along these vectors, your dimensionality goes from d to k. So you can think of this matrix as a transformer of your dimensionality from d to k. Okay, so that's how it works. And the good thing about this is that it's reversible as well. So we can approximate the original data point. So let's say if you got a point x and we projected it using our matrix W to a new space. So let's say if this was a d-dimensional point, then we use this W matrix and we converted it into this Z, which is now a k-dimensional vector. Then I can go back by inverting this transform, okay, and multiplying this Z with W inverse. And the good thing about, as I've shown you earlier, is that W inverse is actually equal to W transpose. So what that means is that I'll be able to approximately reconstruct a d-dimensional data point corresponding to a given point after PCA projection. And this is how you can do that. Now, this is not going to be perfect, because unless there are certain conditions are satisfied, but in general, whenever you do dimensionality reduction, you lose some information. So there's going to be some information loss between this reconstruction and the original data point. And we can calculate that by just simply taking the norm of the difference of these two before and after projection. Okay, so we can do that. We can also do reconstruction. Okay. However, in certain cases, when your dimensions are very large, then the computation of covariance matrix can be very difficult. So let's say if you got D is equal to, let's say, 10,000, then your covariance matrix is going to be of size 10,000 by 10,000, which is going to be not fit, which is not going to fit into memory. So we have this other method, which is called the snapshot method, or snapshot implementation of principal component analysis, that you can use. I'm not going to go into too much detail of this method, but it's essentially an equivalent way of doing principal component analysis in which you don't end up with, so in the original PCA implementation, you had matrices of size d by d when you were doing the covariance matrix calculation, right? And if d is large, this is not going to fit into memory. This snapshot method constructs an equivalent covariance matrix that I'm going to indicate with C, with this weird tilde sign on top. That is going to be of size n cross n. So if n is much smaller than d, then you can use this method, okay? So if you are working with images with a very large dimensions, but with only a small handset, small number of images, you can try this snapshot method out, okay? There are other variants of PCA as well. One of them is called incremental PCA, which builds these principal component bases incrementally, and it's available in sklearn. One of the issues with a PCA is that it's not robust. So what that means is that, let's say if you got a data set like this one, but you have one point that is far away from this, then the basis that you're going to get is going to be disturbed by the presence of this outlier. So this is the problem with the original principal component analysis. Robust principal component analysis is the way of overcoming this problem so that we end up with this direction rather than paying too much attention to outliers. So if you suspect that your data may have outliers, use robust principal components, and I'll be posting some resources on that. Because principal component analysis involves dot products, because it's essentially a projection, then that means it can be kernelized, and there are kernelized variants of principal component analysis as well. We're not going to cover them in this module, but just for your information, they are available. Okay, so that's pretty much it. Everything about principal component analysis. The rest of it is you can study it in terms of you can read more about principal component analysis in the notebook that has been given to you. Okay, thank you.